Hello, all of you. Welcome to the 8th lecture on the course on analysis and modeling in chemical engineering. In this week, we have been doing a quick revision of the fundamental laws and concepts in chemical engineering. I started with equation of motion and transport equation in the 6th lecture, and then we did material energy balance in the last lecture. So today, I want to come to one of the most interesting and important subject of chemical engineering, that is thermodynamics. And what I want you to kind of see from the discussion is how this kind of connects with every other concept that you will learn in chemical engineering. So I want to look at thermodynamics in a way that is probably more like along the theme of this modeling course, and that is to begin with the equation of motion again, right, or the conservation of energy, to be more precise. So what we want to do here is just to begin with the same ball experiment. I have done a version of that earlier. There the ball was going down in a viscous liquid, to an experiment of simply a ball falling from a certain height in the natural air, just like what Newton actually saw when there was an apple falling from tree, something very similar to that. So I will start from here, and then I will take from here to the actual thermodynamics. So this actually builds up from what is to come. This is not quite thermodynamics. This is the definition of just energy and work that is applied to in general context, but we'll come to thermodynamics, but starting from this basic idea of energy and work. Right? So let's imagine that you have a ball that starts from a certain height h, let's say, where the kinetic energy of the ball is 0, that means it's stationary, and let's say it is dropped from there. Maybe it can be third floor of a building. So at that point, there is a potential energy available in the ball, but the kinetic energy is equal to 0, right. So it starts from here, and then it comes down and it hits the ground, right. And let's take a point before it hits the ground, because once it hits the ground, it will rebound, and then whole lot of things will happen. So we want to just see before it hits the ground, maybe. So you start from some height h and maybe stopping just before touching the ground, right. So what is going to happen is, once it reaches near to the ground, the potential energy is will come close to 0, because the height whatever we started with, now I am at almost no height, but the kinetic energy is much larger, right. So what exactly happened here? Once this ball was falling down, the kinetic energy was gradually increasing. The ball became faster and faster over time, and potential energy gradually kept decreasing. In other words, potential energy change gave rise to a change in the kinetic energy, or we can say that the net energy of the system kind of remained constant. Potential energy came down, kinetic energy gone up. And in fact, the same argument more or less we have used when we used Bernoulli equation in the previous example, and we established that the velocity is under root 2 gh, right. Different context, but the Bernoulli equation essentially is again the energy conservation equation. So therefore, we'll pretty much get the same equation if I just assume that the change in the potential energy, that is mgh, is equal to the change in the kinetic energy, that is half mv square. Of course, one is a positive change, other is a negative change, but if I do that, I am going to get v underscore v is equal to under root 2 gh. Right? But when we first define the energy, we typically define it like energy is the ability to do work. What work happened in this system? If you think about the ball as a system, and unless you think that somebody threw the ball, let's say a baller with a certain energy, external energy, in this case, there was nobody doing the work on the ball as such. If you think about it, the energy remained constant. So there is an ability of doing work in principle, but in this case, it is not about that. It is about the change of energy from one form to the other. Potential energy converted into kinetic energy, right. So in this case, if you think about it, no one did any work. If you think the ball as a system, you simply can say that the energy remained constant. One form of energy converted into other form of energy, right? So, in order to define the work, we need to think about the influence of an external agent on the system, typically speaking, right? So, let us say now I take another example, and we are playing a game of carom board, and now there is an external agent, let us say a striker, that is being pushed by a player, and now the striker hits one of the pieces on the board. So, then there is going to be an external agent, which is the person playing the game, and that energy, whatever he is providing, that force that he is providing, gets transferred into kinetic energy of the striker, and then the striker hits another piece, and the kinetic energy of this is used to basically move the other piece. So, kinetic energy of the striker will reduce and kinetic energy of that piece will increase, and now it will go like forever, right? Again, if you think about this two pieces in the game, maybe a striker and the other piece, or any two pieces in the game, and if I take both as the system, right? Let us say there are two pieces, a red and a yellow one, and I am saying that they are moving with a certain velocity to at a particular time, right? Of course, they will collide, and once they collide, they will exchange momenta, and they will move with different velocities. So, maybe they came with velocity u1 and u2 in the first place, and after collision it becomes v1 and v2. Again, we will say here that the energy of the system remained constant, because I have taken both of these pieces as part of my system, right? That is, I am considering like two pieces moving. Of course, in the beginning somebody gave some kinetic energy in the system, right? So, that could have been assumed here, but you see the way I have defined it, I began from a point where the velocity was already there. If I begin from that point where the striker already has a velocity, let us say u1, and the piece may already have a velocity u2, in the beginning it can be 0. Then after collision, they have momentum transfer, they acquire some velocity, we can write equation of motion, we can write the conservation of energy and things like that, and we can assume still that the energy of system is a constant. However, if I now define only this red guy as my system, and I say that yellow guy is my external agent, that is applying a work or doing a work on the red guy. So, now clearly the energy of this red guy is changing here. Unlike the previous case, the energy of the entire system was constant in the previous case. Now, if I look at only the red ball, then clearly its energy is changing. Earlier it was something like half m u2 square, and now it is something like half m v2 square, right? And this energy change is caused by what? This energy change is caused by the external agent, which is the yellow ball here, right? So, the first lesson that you have to get in thermodynamics in general is, whenever we define energy and work, we need to be very clear what is a system and who is doing work. Typically, in thermodynamics, we take the notion of system and surrounding, and the surrounding is something that is around that system, that is doing some work on the system or applying heat or whatever, right? So, we have to have a clear definition of that surrounding or the external agent which is doing something on the system, right? At the same time, the system itself can do some work on the surrounding, and that also has to be defined in a proper way by defining the system and surrounding properly. Okay. So, now I now take a more complicated system, and now I will consider actually what is known as a thermodynamic system. So, I will consider molecules. In some approximation, the molecules can also be taken as balls. In fact, molecules have a certain shape and size, right? But that is quite vague. Let us say water molecule. So, you have oxygen and two hydrogen. That is a simplistic drawing, but it is not that. If you look through a microscope, you will see two sticks connecting oxygen and hydrogen. What you will essentially see is some kind of an electron cloud, a cloud containing some charges and things like that, right? But in the approximation of classical mechanics that we sometimes take, that is used in thermodynamics, we consider these molecules as some sort of balls. We can assign them some shape, but to begin with, let us assume them some spherical balls, right. So now, as I have said earlier, when I did in the context of colloidal system, there may be interparticle forces between them. And now I am talking about molecules. So they are fairly small, very much smaller than even the colloidal particles, right. So clearly interparticle interactions are very important here, and therefore I will assume that there is no external influence to begin with. Already the system is fairly complicated. We have interparticle interactions, and they exist between every pair of particles or molecules in the system. So any particle is getting a force from every other particle in the system, right. It's fairly complicated. So I will assume that there is no external influence. That means the surrounding of this system, let us say I am considering a system, they will have other things around it. The surrounding of that system is not doing anything on that system. No kind of work, no kind of heat, no kind of mass exchange or anything of that sort, right. So if I do that, essentially what I am defining is what is known in thermodynamics as an isolated system. There is no mass exchange with the surrounding, and there is no energy exchange with the surrounding, right. Although it's easier to define, it's difficult to achieve in practice, right, because you can think about it. Let us say I have a glass of water kept here, then clearly the glass of water will exchange the energy with the surrounding. If it is hot to begin with, it will get colder. If it is cold to begin with, get hotter depending on the room temperature, right. I can of course take a bottle that is insulated and I will have water inside, but no insulation is perfect insulation. Over time, even if we begin with a hot water in a thermos, it will get colder, and a cold water will get hotter. So the energy exchange may always happen, no matter what is the rate of energy exchange. To say that the surrounding is not doing any influence, not having any energy exchange and any mass exchange, is something that is literally not possible, but it can be assumed, at least theoretically speaking, or at least for systems that are heavily insulated, it cannot be, it can be a good approximation as well. So now the kinetic energy of this system, that is a system under no external influence, is the sum of the kinetic energy of all the particles, in this case molecules, in the system, right. Let us say the particles are all identical, so they have some mass m, and let us say n is the number of particle, and Vi is referring to the velocity of the ith particle. So the kinetic energy of the ith particle is something like half m Vi squared, and if I sum it over all the particles, right, by the way there should be no n here, if I sum it over all the particles, right, we will get something like this, where this average V square is the average squared velocity of the particles, and that average V square is assumed to be proportional to the temperature of the system. In fact, temperature is defined in this particular way. When I say the system has a temperature, what I essentially mean is there are molecules in the system that has a velocity, and temperature is proportional to the average of the square of the velocity, right. Okay. So now strictly speaking, from kinetic theory of gases and using the idea of what is known as an equipartition theorem, we can define the kinetic energy as something like half multiplied by n kBt, where n is the number of molecules and F is the degree of freedom of the molecule. That is, how many directions it can move, or how many kinds of movement it can do. For a monoatomic gas, the three movement possible are translation in the three directions, and that give rise to something like 3/2 nkbt here. If it is diatomic, then it is 5/2, and if it is more complicated, you will have some other form, because the degree of freedom is changing here, right. But the key idea is that the average V square is proportional to temperature, right. In addition to this kinetic energy, the system also has a potential energy, right? And that is because of the interaction between the particles. Again, I emphasize, for molecules, gravity or buoyant forces or viscous forces, they are not very important, right? So the only energy that we are considering are the interparticle energy, apart from the kinetic energy, right? That too, if I assume it's an ideal gas, we assume that the particles are non-interacting, and then we can assume that the potential energy is equal to 0. And then the total energy of a system, that is what I know as the internal energy of a system, that is defined as something like this, right, for an ideal gas, right. So half kBT per degree of freedom for a molecule. So half kBT F is the total energy of one molecule, and we have n molecules, so half n kBT F, right. Keep in mind that whenever I say total energy of a molecule, I am saying in the average sense. Of course, molecules may have different velocity, but we are talking about the average of the squared velocity in this picture. Okay. So now, if I take the system to be isolated, this energy has to be constant, because who is there to do the work? As I was telling you in the example of the ball falling, the energy was constant. There was a transformation of potential to kinetic. And the carom board problem, if I consider both pieces as the system, then nobody is doing the work on that. So the energy that therefore is constant, right? So again here, there are things happening in the system. The particles are moving, they are colliding, it's quite vigorous, but there is nobody to do any work. The surrounding is not interacting, not influencing the system. So therefore, we can assume that the energy is constant, right, for this system. Okay, but there is other thing that is happening in this case, that is the idea of entropy, right. And the way it has been introduced in undergrad may be different from the way I am defining it, right. But what must have been taught is entropy is a measure of randomness. What exactly is randomness? So again, I will take this molecular level picture, and let us say you have some energy E of this entire system, right. Now that energy is of course distributed among the particles or the molecules in the system. And I was telling you that the kinetic energy can be different, the velocities need not be same. For the purpose of temperature, we are talking about average of V square, not the actual velocity of every particle in the system, right. So therefore, the energies can be different, and we may imagine that there are some I particles with some energy epsilon I. So if I sum over Ni epsilon I, so Ni particles are having energy epsilon I. If I sum it over all possible value of epsilon I will get total energy of the system, right. Now you may say that okay, energy is a continuous variable, but it is not. Energy is a discrete variable, because quantum mechanics tells you that energy actually exists in packets or quanta of energy, right. And that basically comes from the notion of quantum mechanics that I will not get into. But the key idea is energy is defined in terms of energy levels. You can be in the ground state, or you can be in an excited state, or even more excited state, and things like that, right. The key idea is that energy is not a continuous variable, it's a discrete variable. It exists as multiples of some quanta. But again, I mean, since the magnitude of that quanta is very small, the number of quanta that is typically available in a system is very large, right. And therefore, in the usual language, we therefore treat energy as a continuous variable, but keep in mind that energy in fact is a discrete variable. It exists in multiples of some quanta, right. Just to simplify the picture, let us say, for example, if you have the smallest possible energy is epsilon, then the energy of a system is something like m multiplied by epsilon, that is total energy available in the system, right. Of course, there are assumptions made here, right, but this energy is getting distributed among particles in the system, and that distribution need not be uniform. In fact, it will not be uniform, as I will demonstrate. So therefore, I can define a quantity that can actually be a measure of how I am distributing the available energy into the particles or molecules in the system, right? And let us say W refers to the number of way of this distribution. Then I can define a quantity S is equal to Kb ln W. What is more important is S is proportional to ln of this W, right? That will be measure of some quantity that I will call entropy, right? And this should be something, this should be useful for us. Otherwise, what is the point of defining a variable, right? And we'll see like how useful it is, right? So there is, it's attributed to a scientist named Boltzmann, right? So there is a prefactor here that is called the Boltzmann constant. And in fact, just to put things in perspective, this Boltzmann factor actually is the gas constant divided by the Avogadro number, right? There is a reason why S is written as ln of this W, right? And you can look up about it, but you will see in the coming lectures and this lecture how this idea of entropy is useful. Okay, so before I go further, let me put across this point with a simple example, right? So I have said that the energy is discrete, energy is quantized, it exists in packets, right? And let us say I take this packets as like chocolates, which I am distributing among students, right? So let us say, for example, there was 3 quanta of energy available in the system, 3 packets of energy available in the system, and there are 3 particles. In the thermodynamic system, you will have very large number of molecules. But just to start with, I can assume that 3 quanta of energy, 3 packets of energy, all of same quantity, available for distribution among 3 particles, right? Now that problem is somewhat similar to distributing 3 chocolates among 3 students, right? And the question I want to propose is, what is the number of ways in which I can distribute this, right? And now you can imagine that if I have 3 chocolates, it can be distributed among 3 students in multiple ways, right? What we would think as most justified thing is I will give 1 to everyone. Let us say there are 3 students, A, B, and C. Everybody gets 1, right? The other possibility is that one of them gets 2, the other one gets 1, and the third one gets none. Another possibility is one of them gets 3 and other 2 gets 0, right? So all this possibility does exist. Now the question is, which of this should happen? I mean, in the ideal world, if it is very judicious, if everything is happening fairly, then you may imagine that the first thing will happen because it should have been an even distribution. But in molecules, that is not the case. Energy is not fairly distributed. The reason being that the number of ways in which this can happen is lesser than the number of ways this can happen, right? I can demonstrate this. So let's say, for example, I am doing the case where everybody gets 1, right? And keep in mind that the molecules are indistinguishable, right? So who gets 1 is not the point. The point is everyone gets 1. So I'm not differentiating between who is getting what, right? So now how many ways it is possible, right? So in this case, if you have to think about it, the number of particles having 1 chocolate is equal to 3. The number of particles having 2 chocolates is equal to 0, and the number of particles having 3 chocolates is also equal to 0, right? The net energy is sum over Ni epsilon I. Now in our case, epsilon is the measure of the number of chocolates, right? So I can look at it like this: 3 into 1 plus 0 into 2 plus 0 into 3 is equal to 3. So the net energy is 3, but in this particular distribution, all of them gets equal to 1, right? So, if I want to find the number of ways in which this possibility can happen, it is given as something like this. So, W is given as the n factorial, that is the number of chocolates which are available, divided by number of particles having one chocolate, number of particles having 2, and the number of particles having 3. By the way, this n is not the number of chocolate, it is the number of particles or students in this case. So, what we get here is this is equal to 3 factorial by 3 factorial, 0 factorial, 0 factorial, plugging in the values of n1, n2, and 3, and that is equal to 1. On the other hand, if one person gets 2, in that case the other person gets 1. So, number of people having 1 is equal to 1, number of person having 2 is equal to 1, and number of person having 3 is equal to still 0, right? But number of person having now 0 chocolates is equal to 1, right? So, again I could have had that n0 here as well, but it won't make any difference, right? So, now you will see this W is going to be something like 3 factorial by 1 factorial, 1 factorial, 1 factorial, 0 factorial, right? So, I am considering having number of people having 0 chocolates, number of people having 1 chocolate, number of people having 2, and number having 3, and this gives me 6, right? So, in one way it is possible that everybody gets 1, and in 6 ways it is possible that one of them gets 2, which is having a higher probability therefore than the previous case, right. So, the point is that entropy dictates what is more probable. Entropy dictates what is more probable, and therefore it is more likely that you will have unfair distribution of chocolate than compared to a fair distribution, right. I can go ahead and do the third case where one person gets 3. So, in that case we will have number of people having 0 chocolates is equal to 2, number of people having 1 chocolate is equal to 0, number of people having 2 chocolate is still 0, and number of people having 3 chocolates is equal to 1, and that gives me W is equal to 3 factorial by 2 factorial, 0 factorial, 0 factorial, 1 factorial is equal to 3, and that is of course less than 6, but is still more than 1, right. What this means is if I do this kind of an experiment 6 times, you will find that you are going to have one student having 2 chocolate and other 2 having 1 and 0. Only 3 times we will find that one of them gets 3 and other 2 do not get anything, and 1 out of 10 times you will have a fair distribution of chocolates. So, a fair distribution of chocolates is much less likely compared to an unfair distribution. So, how does this idea apply, right? So, let us say for example, I start another experiment, very different context, right. So, I have 2 compartments, in this case chamber A and chamber B, and in the beginning I assume that you have some n molecules in the chamber A, that is the first compartment or left compartment, right. And I have a complete vacuum on the other side, and there is some valve that is closed here, that is ensuring that no molecule can go from chamber A to chamber B. Now, at time t equal to 0, I open this valve, and now the molecules can flow from here to there. Now, as soon as I tell you this, you may recall that concentration gradient drives mass transfer. So, therefore, molecules should go from left to right. But what I am telling you is that it is nothing to do with the concentration gradient in this case, or the more fundamental reason in this case is not the concentration gradient, it is purely coming from entropy, right. So, if you think about the case where the molecules after opening the valve do not go to the chamber B, right. So they have an option of going in chamber B, but let's say they prefer to remain in chamber A, right? So now they can of course keep on moving within chamber A. So they have, every particle has a volume VA available for them to move. They cannot go to chamber B, but they have a volume VA to move within chamber A, right? So therefore, the number of ways they can do this kind of movement within the chamber A is VA to the power n, because every particle has a room of VA available, right? So two particles, if I think about the number of ways, it is VA into VA, VA square, right? So for n particles, if I find the number of ways in which the particles can get distributed within chamber A, it is VA to the power n, maybe some prefactors, but are not very important. On the other hand, if they go to chamber B, at least some of them go to chamber B and others remain in chamber A, in that case, every molecule gets more room to play around, right? And let us say this is happening uniformly. Every particle can basically go to both the chambers. Then the volume which is available for them to move around is VA plus VB, right? So clearly, the number of ways that you get here, therefore, VA plus VB to the power n is much, much higher than VA to the power n, right? So the molecules are going from the left to the right purely from entropic considerations, because I told you also that S is equal to Kb ln W, right? And entropy has a tendency to favor more number of ways, because the system wants to maximize its entropy. In the previous case, we preferred the case that gave me W equal to 6. That was unfair distribution, but it gave me more ways. So therefore, we preferred that. So whichever gives me more number of ways, I will prefer that, right? And ln of that number of ways is the entropy. So we will basically go for higher entropy cases. So essentially, we will try to therefore maximize the entropy, and entropy will get maximized if every molecule can go from here to there and vice versa. If they can freely move around in the two chambers, every molecule has more room to play. The number of ways of putting a molecule goes like VA plus VB. On the other hand, it goes like VA. So for n molecules, it is VA to the power n in the previous case, and VA plus VB to the power n in the next case, and therefore there is going to be an entropy change as soon as you open the valve, right? As soon as you open the valve, in the beginning, the W1 was VA to the power n, so the entropy was something like Kb ln W1, and after that it is something like Kb ln W2, and therefore the entropy change S2 minus S1 is Kb ln W2 by W1, and that gives me something like this, and that is a positive number. Why? Because VA plus VB by VA is higher than 1, so this gives me a positive number. So if the entropy change is positive, system is actually increasing its entropy. So whatever increases the entropy, that determines in this case the direction of mass transfer, right? So yes, there is a concentration gradient that drove the mass transfer, but the fundamental reason for that is not the concentration gradient, but the fundamental reason is that this movement resulted in an increase in the entropy of the system, right? And in fact, if it is a very fair distribution and the molecules can pretty much go in both compartments freely, then the probability of a molecule to remain in chamber A is proportional to the volume of chamber A, because it has, the room is VA, right, divided by the total volume available in there, right. So for example, if VA is much less than VB, then if the molecule remains in the compartment A, it has a much lesser room. If VA is much less than VB, right, it will go to the other compartment, right, because there is more room there. So whatever gives you more room, it will go there, because that increases the number of ways, right. So therefore, the probability of a molecule to be in chamber A is given by Va by Va plus Bv, and same for B. So, the number of molecules in chamber A by total number of molecules is Va by Va plus Bv, and number of molecules in chamber B by total number of molecules is Vb by Va plus Vb, right. In fact, we can go ahead and use this idea of how entropy drives mixing. Let us take an example of nitrogen and oxygen, and I assume both are ideal gas, and let us say I put them together, right. So, I open a nitrogen cylinder and an oxygen cylinder and let it be, right. So, now they have an option to either mix together or they remain separate as nitrogen molecule and oxygen molecule, right. And this mixing again is purely happening because mixing increases the entropy of the system, right. So, if they do not mix together by the argument which I gave you, the nitrogen had a number of ways proportional to the volume of nitrogen, which is Va to the power Na, that is the number of molecules of nitrogen, and oxygen had a number of way proportional to the volume of oxygen to the power of the number of oxygen molecules. And if they mix together, now they share this total volume Va plus Vb for Na plus Nb molecule if they mix together. So, the number of ways will be therefore Va plus Vb to the power Na plus Nb, right. And again I can find the entropy change for this happening, right. And what I then find is my entropy change is something like this. And if I define my mole fraction of A as something like this and mole fraction of B as something like this, and it is an ideal gas, so mole fraction is equal to the volume fraction, right, and mole fraction is clearly less than 1. And if I simplify the expression, I get a term like this, and this term has to be negative because Xa is less than 1, that goes in the ln here. So, this term must be negative, but there is a negative sign appearing here. So, delta S is positive. So, entropy is increasing if they mix together, and therefore, at least for the gases, they will always mix together, right. Of course, for every statement that I am going to make, in every statement I make, there are certain limitations or points to be considered again, and I will discuss those points in the following classes. So, with that, I want to summarize my discussion. We have started talking about thermodynamics. I started with the simple example of a ball falling to demonstrate the concept of energy and work and system and surrounding. And then we went to a thermodynamic system which was isolated to demonstrate the idea of temperature and the interparticle interactions. And finally, we demonstrated the idea of entropy. I began with the simple energy distribution by analogy with the distribution of chocolates, but then I went further of how it is useful to demonstrate that entropy is something that actually drives mass transfer or mixing in a system. So, in the next class, I will continue talking about thermodynamics in more detail. So, with that, I want to stop here. Thank you so much.